everyone! Today, our group will talk about a real-life application of mathematics by looking at the seating arrangement in an amphitheater and how it relates to arithmetic sequences. An amphitheater is a place used for performance or lectures where the seats are arranged in curved rows facing a stage. The seating is designed so that each row is placed slightly higher and wider than the one in front. This allows everyone to see the stage clearly and hear the sound properly. As the rows go further back, the number of seats increases because each row becomes longer and can fit more seats. So, why does the seating arrangement of an amphitheater form an arithmetic sequence?
Now that we understand the layout of amphitheater, let's look at the mathematics behind it. To determine how many seats are in the specific row, we use an arithmetic sequence, which is a list of numbers where the difference between one term and the next is always constant. In our amphitheater, this constant represents the extra seats added to each row as the circle widens. To calculate the number of seats in any row, Tn, we use the formula Tn equal to A plus n minus 1 times T. In this formula, A represents the first term of or the number of seats in every first row. Variable n represents the specific row number we are looking for, and D is the common difference, which is the fixed number of the seats added to every subsequent row. For example, if our amphitheater starts with 20 seats in the first row and each row behind it adds 4 more seats, we can easily find the seating for row 10. Instead of counting them one by one, we calculate 20 plus 10 minus 1 times 4, which tells us there are exactly 56 seats in that specific row. While knowing the seat in one row is helpful, a manager often needs to know the total capacity of the entire venue.
From the previous part, we know that the number of seats in each row of an amphitheater forms an arithmetic sequence because the seats increase by a fixed number in every row. Now I will explain how to find the total number of seats using an arithmetic series. An arithmetic series is the sum of all terms in an arithmetic sequence. In this context, it represents the total seating capacity of the amphitheater.
Sn equal to NO2 bracket 2A plus bracket n minus 1 times D, and Sn equal to NO2 times A plus L, only if the last term is known.
This formula allows us to calculate the total number of seats without adding each row one by one.
Now that we understand the math behind arithmetic sequence and series, let's bring it back to our amphitheater. Why does any of this matter outside of the classroom? In a real-world design context, the arithmetic sequence is what describes the seat in each specific row. For example, if we need to know exactly how many chairs to order for the 10 row, we use the sequence formula Tn equal to A plus in bracket n minus 1 times T.
Exactly, but when we talk about the arithmetic series, we are looking at the bigger picture, the total seating capacity. In the real world, investors and venue managers don't just ask about one row. They ask how many people can this hall accommodate, or what is the maximum capacity for tonight's show. By using the sum formula, Sn equals to n over 2 times 2a plus n minus d times d, we can calculate the total capacity of a massive stadium in seconds rather than counting every single seat one by one.
Now we are looking at the example of arithmetic sequence and series in a real-world analogy. Imagine we are designing a section of a stadium. In this section, the front row starts with 20 seats. Because the stadium widens as it goes up, every row behind it has exactly 4 more seats than the one before it. If a guest asks, how many people can fit in row 10? We don't need to go upstairs and count them one by one. We use the term formula Tn. Row 1 have 20 seats, row 2 have 24 seats. Following the pattern, row 10 will have exactly 56 seats. The total of row 1 until row 10, we will get 380. Now, suppose a ticket manager needs to know the total number of seats available for the first 10 rows combined. This is where we use the sum formula, and we will get the same answer, which is 380 seats.
This brings up an interesting conceptual link, convergence. In a theoretical infinite sequence, number might grow forever, but in real-life architecture, a series must converge or settle at limit because physical constraints like length size, safety codes, and acoustic. You can have an infinite number of rows.
To conclude, arithmetic sequences and series aren't just numbers on a page. They are the language of efficiency. They allow architects to maximize visibility and capacity, ensuring that whether you are in the front row or at the very back, the geometry of the room is working for you. The next time you sit in a stadium or a theater, remember you are sitting inside a mathematical series.